Okay, so we'll speak about multi-determinant wave functions in QMC. So, so normally when you make a CI calculation, you try to optimize here the CI coefficients that are here in front of the determinants. So these are the parameters that change along the calculation. So if you have, let's say, 100 million determinants, you will need to optimize 100 million parameters, and this will change. In QMC, it's a bit, when you compute the energy, the variable is no more the CI coefficients, it's really the electron coordinates, okay? So when you make a QMC simulation, these coefficients are fixed, so it's the cost will not necessarily be the same. And making a QMC calculation of a CI wave function is expensive, because at every step, every time you move the electrons, you need to compute, you need to evaluate the wave function, its gradient and its Laplacian at the electron positions. And so you need to evaluate all the Slater determinants at every step. So this can be very expensive. And this is why you want to have a compact expression of the wave function, trying to reduce as much as you can the number of Slater determinants, and to make the cost of the calculation really as cheap as you can. So how do we evaluate determinants at the electron positions? So we build the Slater matrix. So the Slater matrix is a matrix with the molecular orbitals evaluated at the electron coordinates, okay? And when you calculate the determinant of this matrix, it is the Slater determinant. So, so how do we compute on the computer the determinant? So we usually, when you don't have any information and you have just a matrix with numbers, the standard method is to do a LU factorization, and then you can compute easily the determinant, and the cost, the total cost is n to the cube, where n is the number of electrons. So remember, here you need to do one Slater matrix for the alpha electrons and one Slater matrix for the beta electrons. So the n here is not the total number of electrons, it's the number of alpha or beta electrons. And so, so once you have done the LU factorization, the determinant is just the product of the diagonal elements. So now, so I said you needed to compute the derivative of the wave function. So to compute so you need here the gradient of the wave function with respect to the electron coordinates. So this is needed for the DMC algorithm for the calculation of the drift. Also for the VMC if you do drift diffusion. And here you need also the Laplacian, because you want to compute the kinetic energy, so you need to calculate the Laplacian of the wave function. And to evaluate the Laplacian of a determinant, you can use this formula, where you can compute easily Laplacian of a determinant divided by the determinant, and you can evaluate it like this, where Laplacian I phi j is you take the Slater matrix like this one, but here instead of inserting the matrix, the molecular orbitals evaluated at the electron positions, you evaluate the Laplacian of the molecular orbitals at the electron positions. And similarly for the gradient, this matrix is really the matrix where you have the gradient of the orbitals. And you need to multiply these elements by the inverse of the Slater matrix. So you need also to inverse this Slater matrix, and so it costs also n to the power 3. So basically at every step of your QMC simulation, you need to do an n to the power 3 calculation. So this is the standard way. If you move all your electrons together and you have a determinant every time, you need to evaluate the determinant. The cost is n to the power 3. So we don't do that in practice because n to the power 3 is expensive. So we use instead the Sherman-Morrison-Woodbury formula. And so this formula says that if you have already the inverse of the matrix A, and you make a little modification to this matrix A, you can update the inverse. Okay, and the cost of the update, if you update a row, a complete row, or a column, it will be n squared instead of n to the cube. So let me just show you what this is. So A is the original matrix. U V transpose is the outer product of a vector U and a vector V. Okay, so as it's an outer product, it will make a matrix. And so this is how you would encode the change in A. So for example, if you do a single orbital change, your vector U will be, so suppose you substitute the orbital L by orbital K, UV will be the outer product of this vector where you have the orbital K minus the orbital L, because you remove L and you insert K instead. And here V will be a vector where you have 0 everywhere, except you would have a 1 here to describe at what column index you will make the substitution. Okay, so here the 1 will appear at the position where you had the phi L in the A matrix. And so so doing that, you would update the matrix A quite easily, and then to update the inverse, you would just apply this formula. And if you look, it's really n squared. So this is really to update, so let me come back. It's to update the Slater matrix and its inverse. And I told you that you had one for the alpha electrons and one for the beta electrons. So the important point also is that when you write your wave function in the CI expansion, usually here D represents a Slater determinant. So it's a determinant with all electrons inside alpha and beta. And I told you at the very beginning that the Slater determinants could be expressed as a product of an alpha determinant and a beta determinant. And so this expression can be rewritten like this, where you express each Slater determinant with a product of an upspin determinant and downspin determinant. And between two different Slater determinants, you could have the same alpha part or the same beta part. So there are different, what you need to do is really identify the unique alpha parts and the unique beta parts and see how you will recombine them all together. So if you identify by I the upspin determinant and J the downspin, then your CI vector, you can re-express it as a matrix Cij like this. And the dimension of this matrix is number of upspin determinants times number of downspin determinants. And in the case where your wave function is a full CI, okay, this number here will be the square root of ND, and this one will be also square root of ND, such that the product of the two gives ND. Okay, and so as I said, in the QMC simulation, what is changing is the electron coordinates, not the CI coefficients. And so this transformation can be done as a preprocessing step. And then you can use this form of wave function at every step of your Monte Carlo simulation. So I see here that there is a question in the chat. Okay, no, a question. So do you have questions about this right now? No? Okay, so clear. Okay, so now let's let's see how we can compute this in an efficient way. So, as I said, at every Monte Carlo step, you need to evaluate the wave function, the gradient, and the Laplacian. And you need also to evaluate the non-local component of the pseudo-potential. So
maybe, Anthony, I can interrupt.
Yes.
There's a reminder about a question which maybe hasn't been addressed yet.
Mm-hmm.
It's in HackMD now. So this came from last week, I think. It is possible to have the code use unrestricted Hartree-Fock wave functions, but not in an automatic manner. We can discuss it on Monday. But has it been answered? This question?
Okay. So I can answer this one. So yes, there is no problem using unrestricted Hartree-Fock. So you can always do it with every QMC code, because the only thing you need to do is to have different orbitals in determinants di than determinant dj. Okay, so in all the codes you can always specify that you have twice the number of orbitals. You can concatenate the alpha and beta orbitals, and then you can say here that the first determinant you fill it with the first orbitals, and the next one with the other orbitals. So there is normally no restriction in any QMC code about this. So I was saying you need to compute the wave function, the gradient, and the Laplacian at every Monte Carlo step. And remember, we are using this kind of expression. So you see here, di of r. This is a vector of size number of upspin electrons, and this is a vector of size downspin electrons. Okay, so this Cij di dj can be expressed like this in matrix form, where you have a vector transpose, a matrix, and a vector, and this will give you a number which is the value of the wave function. Okay, so now to evaluate the gradient, you see you can have here a little matrix which is the gradient of the d up vector multiplied by cd down, and so this will be the gradient for the upspin electrons, and the gradient for the downspin electrons will have this expression here, where you apply the gradient only to this part and multiplied by this. The Laplacian has the same kind of expression, but instead of having the gradient here, you have the Laplacian. And similarly, for the non-local pseudo-potential, you have the non-local pseudo-potential operator acting on the upspin electrons here or on the downspin electrons here. So it's always the same kind of expression. And you see that here you have some common intermediates that are C multiplied by the D down vector that you can reuse here, here, and here, and D up multiplied by D up transpose multiplied by C that you can use here, here, and here. And these are necessary for the computation of the wave function. So what you would do, because when you multiply a matrix by a vector, it gives you a vector, you would do the multiplication D up C and CD down once for all at the very beginning. Then you would get the blue and red vectors, and then you just do this. So this is a small matrix. It's a 3 by an electron matrix. So you just do these little matrix vector multiplications. And the important thing to visualize is that the only step that depends on the total number of determinants is this one, okay? Because here the number of operations will be proportional to the number of non-zero elements of C, which are the total number of CI coefficients. But here, once you have contracted C and D together, then these operations, gradient, Laplacian, and pseudo-potential, they don't depend on the total number of Slater determinants, but they only depend on the number of upspin and downspin determinants. So this is what I try to represent here. the calculation of the d up and d down vectors and the gradients and the Laplacian, they cost number of upspin determinants multiplied by number of electrons, upspin electrons squared. Okay. Then you have the only step that depends on the total number of determinants, which is the sparse vector matrix product, which is this one. And you see that this step doesn't depend on the number of electrons. Okay, it just depends on the number of determinants. And then you have the calculation of the other quantities that depend on number of electrons down multiplied by number of determinants up. So basically, if you have, suppose a large CAS SCF wave function with 1 million determinants, you would have here a cost of 1 million, but with a tiny prefactor that doesn't scale with the number of electrons. And here, in this part and this part, will not cost 1 million, but it will cost only 1,000 multiplied by the number of up and down electrons. So you can really bring the cost of the evaluation of the wave function. You can really bring it down by doing the operations properly like this. So this makes it possible to make calculations with very, very large wave functions. And so this is typically what we do with Michel Caffared in Toulouse in our code QMC Chem. So the idea is to use very large CPC expansions as trial wave functions for QMC, and we just run DMC on top of it. Okay, we don't do any kind of re-optimization. We just use CPC as the trial wave function, and we do DMC. And so usually we talk about post-Hartree-Fock methods, and so here, just for fun, we talk about post-full CI methods, where we do the quasi-full CI and then we do the DMC on top of it.
A quick question, Anthony.
Yes.
From HackMD. So how is the spin symmetry preserved in ChIP-C with an open shell calculation?
So with an open shell calculation, so every time you include all the determinants that are necessary to have an eigenfunction of S squared, so the spin symmetry is obtained automatically when you diagonalize the Hamiltonian. It's like it's similar as working in CSF basis. Yes. So let's go back to this. Yes. So here, this is the energy of the water molecule with increasing basis set sizes. So double zeta, triple zeta, quadruple zeta. So here it's 1/n, where n is the CC, PV, NZ. Okay. And so if you go to the infinite basis set, here you cross at 0. So the red curve is the full CI energy. So you see that the full CI energy converts to the exact energy at the infinite basis set level. And if you use the full CI wave function as a trial wave function for QMC, so this is the diffusion Monte Carlo energy that you obtain. So you see that you really gain a lot by doing DMC, and they converge to the same value. And as this curve is more flat than this one is easier to extrapolate here, and so we were able to give a very accurate estimate of the exact energy of the water molecule using this technique. And so in these calculations, we were using up to 1 million Slater determinants. Okay, so now what is the effect of the Jastrow factor on the CI wave function? So if you have a CI wave function and you add the Jastrow factor on top of it, you're not working anymore in the basis of Slater determinants, but you're working in the basis of Slater determinants multiplied by the Jastrow factor. And introducing the Jastrow factor here makes that your basis of an electron functions, they are not orthonormal anymore because of the Jastrow. So this makes the calculations more complicated, because you need to sample the overlap matrix, and when you will solve the Schrödinger equation in this basis, you will need to take into account the overlap of the basis functions. Also, when you add a Jastrow factor on a CI wave function, the Jastrow factor has correlation, and so if your CI wave function has been optimized in the absence of the Jastrow, you will have the same correlation effects that will be described by the determinants and by the Jastrow. So the CI coefficients are no more optimal once you have added the Jastrow. So it's necessary really to re-optimize your CI coefficients in the presence of the Jastrow factor. And when you do this, the effect that you observe is that the Jastrow factor takes account of dynamic correlation, and we have seen at the beginning that dynamic correlation was described by a very large number of small contributions. Okay, and so if you have the Jastrow factor, then the CI doesn't have to take care of these effects, and so the CI only tries to describe static correlation, which is well described by a small number of coefficients, a small number of coefficients with a large magnitude. And so it has the effect of increasing the large coefficients and reducing the small coefficients. So it really compacts the determinant expansion. And as I said before, solving the Schrödinger equation here is more difficult in QMC than with deterministic methods, because here you will need to sample the overlap between the determinant, because your basis is no more orthonormal. And also, you have to keep in mind that these matrices H and S, you have to sample them, so they have statistical errors in the matrix elements, and so you will have noise in when you will try to solve this equation, and also the determinants with very small CI coefficients in the trial function have a very negligible contribution to psi square, and so the matrix elements on those determinants are badly sampled compared to the elements where the CI coefficients are important. And when you have very, very, very small coefficients, let's say 10 to the minus 5 on the CI coefficients, usually the error on the matrix elements is so large that you don't get any information. So really trying to optimize a huge number of CI coefficients with QMC is difficult. But we are lucky because the Jastrow factor really compacts the expressions, and so everything works fine in practice. So now excited state in QMC. So we have seen that the nodal surfaces, they are determined by the determinant expansion, not by the Jastrow, because Jastrow is a positive function. And so if you want to have some accurate excitation energies in QMC, then you need to have a similar quality between the ground state and the excited state, such that the errors you would make would be of the same order of magnitude between the ground state and excited state, and when you make the difference, they would cancel out nicely. So there are two different strategies. So the first one would be to do a stochastic optimization of the ground state and the excited state, but starting from trial wave functions that you would obtain using, for example, KCCF or something which gives a qualitatively good description of your ground and excited state, and then you would re-optimize everything, molecular orbitals, CI and Jastrow factor, all together in QMC. So this is typically what you should have done in the exercises. The other alternative is to do a deterministic optimization. So use a deterministic method that would give a reasonable energy difference using MRCI or CPC, and then run a DMC without modifying the wave function, just considering the DMC as a post-CI method. but so if you do if you do this one, you would get probably lower total energies because you would optimize everything. But here, your energy differences will be sensitive to noise. And in this case here, your coefficients will be optimized insensitively to noise. And so the DMC would be just the error that you would make on the energy will be completely reproducible because it's just conditioned by the initial calculation. So these two approaches, so there are advantages and disadvantages for both. So doing only deterministic optimization, as I said, it's reproducible, so you have a very good quality control. So you have also smooth potential energy surfaces because all your nodes are determined by a deterministic method. But the problem is that for very for large systems, you will get very large expansions, and it will be hard to do for large systems. But for small systems, it's something that works really well. And the stochastic optimization, so it gives you compact wave functions, so it can be applied to large systems. So that's the good point. But the optimization is noisy, and it's harder to get balanced energy, and it needs more. It needs the user to be more careful and to check everything. And with deterministic optimization, you can make it completely automatic. So the two approaches have advantages and disadvantages. And so CHAMP is a very good code for optimizing the wave function. So if you want to make some accurate calculations on large systems, it's probably a good choice. Okay, so then the work we're doing with Claudia usually is to optimize excited states for large systems. So what we call large systems is systems with let's say 15, 20 carbon atoms. So what we do usually, we do a small CFC expansion in a large active space. So this is a way to select a relatively small number of determinants and to have a wave function that is compact. When we do this selection of determinants, we enforce a constant EPT2, a constant correction, perturbative correction at the CFC level for the selection of determinants, such that we expect that the energy difference we have for the variational wave functions is close to the energy difference that we would get at the full CI level. And so this guarantees consistency between the two states. And then we optimize the transfer factor, and we optimize all the CI coefficients in QMC. And then we're able to optimize large systems and calculate the excited states. And so it's important to mention here that this method of optimizing excited states works very well for singly excited states, but it also works well for doubly excited states. And in the cases where the best that you would have is CASPT2, well, this technique is probably more accurate than CASPT2.